In this video, you'll see one of the methods to structure interaction and discussion in small groups. It's called Cooperative Logic. Cooperative Logic's a special kind of problem-solving activity. It's something I learned about from Equals. They were a team of pioneering maths teachers working at Berkeley University in California during the 1980s. Their mission was finding ways of making maths and science more inviting to females and minority groups in schools. The initiative was well funded by the US government at the time. The ideas generated by this project are very relevant in adult numeracy teaching today. Like the other videos in this series, most of the materials can be downloaded from the online resource Building Strength with Numeracy, available through the Velbeck website. And what we're going to do today is look at some things that I call models of activities or activity models, which are fairly simple structures that you can use and say, oh, I could use that structure and I could do this with it or that with it. So they're structures, fairly simple, set rules, different, but hopefully by pointing them out as particular structures and showing you some examples, you can use them to create the things your students need themselves. We're going to start off looking at cooperative logic, which is the most formal of the structures and the most complex. Cooperative logic, it's a small group activity and it relies very much on the pieces in the centre of the table, but it's got really particular rules for sharing, and it's tightly structured in such a way that if you do it properly, everyone has to participate, which is why the rules are important. I'm going to start with the simplest of them. On each table, I'm going to put a problem. We're going to have a map, goes in the centre of the table. We're going to have clue cards, which do not go into the centre of table but are given round to the people. Some people will get 2, some people will get 1. And we're going to have the manipulable pieces. In this case, we've got a map, we've got shops, and we've got clues on how the shops are arranged. The shops are going to be arranged on the map in the shaded area. You use the clues one by one to decide how that's going to happen.
The store and the post office are on corners. How about if we set that one to there? Does that make any sense?
You have to go back and look at
to my one.
One by one, they read them out aloud, but they don't put them down on the table. So others find out what's on the card by actually listening to the person that's reading, not grabbing anybody's clues and not giving away our information. Anyone can read their card aloud as often as is needed until the problem is solved. And so we're cooperatively solving the problem.
The chemist shop is east of the supermarket. East over
Walking from the supermarket to the chemist, you pass the dress shop.
Doesn't necessarily mean it's between. The shop could be there.
That's right. The department store and the post office are on corners.
How about if we set that one to there? Does that make any sense?
You have to go back and look at
To my one, the post office is south of the chemist and next to the shoe shop.
That's good.
What we were listening to there was an example of exploratory speech, working things out or exploring an idea together that results from this kind of cooperative format. It's a welcome contrast to the normal explanatory speech heard in numeracy classes, where one person simply tells the other how to do something.
Southwest, but I actually needed to physically point to the table.
How about if we set that one to there? Does that make sense?
There was an east.
We all right?
We think
Okay.
We're quite.
How would we know that we were all right? for sure.
Yeah, nothing is maybe.
Yeah, so you've checked them all. Yeah. Because I think it's really important with students to get them to self-check rather than expect you to come around and say it's right. You say, can you find out? If you're right, how would you know? So that's important. There's a few things I should say before we move on. One of them, as somebody said, there's a lot of prepositions in there, so there's a lot of language structure that people really need in their lives, that sort of giving directions, walking past and north of and opposite to and all of that stuff. So it's important language going on in there. How did people work out where east was once they had north on the map?
And then there's all the acronyms and little songs. Never eat soggy Weet-Bix and never eat soggy Weet-Bix.
A lot of people use the map of Australia as a reference. You know, eastern states, or what you call the eastern states, but they say Western Australia. So over east we say Western Australia, and it's that way. So east's that way. So yeah. And there's Northern Territory and South Australia, so a lot of people will use the... I always use the nomenclature WE. If that made a word, I got it right. And one other thing that we might take for granted is, that your students mightn't, is that traditionally north has always been the top of a map. So all these things are important to talk about when you do things with their students. So if you open your street directory, north is always at the top of the map, and people mightn't realise that. The first problem, city block, allowed the participants to understand the rules and procedures for cooperative logic. After that, other examples using the language of direction were used. One of these was school fete. Doing clusters of similarly themed problems like this allows students to consolidate their understanding of the concepts and the language. Okay, same structure, cooperative logic, same rules, different problem.
What have we got this time? Oh, these are market stalls. That's good. Oh, okay. Hot dogs, plants, lucky wheel. When Sylvia arrived, she saw the clothes store on her left. She arrived at the entrance. She saw the clothes store on her left. Does that mean it's right there? Immediate. From the entrance, she may still see it on her left. See it on her left. There's something about that that implies it's close to the entrance.
A much more advanced problem was also used so that these teachers could experience how it feels to be totally engaged with a problem that challenges them. There are two of these authentic street directory activities involving maps and keys published in Breaking the Maths Barrier. They were originally designed to encourage literacy teachers to focus on street directories and the knowledge and skills their students needed to know how to use them. You can see how much these teachers had to concentrate to solve the problem.
So the car's sped along Bishop Street. Yeah, going north-south. Okay. Doesn't it say near the corner? Near the corner.
Or the car travelling west past the school.
So there. And then we've got him going past the other ones.
Well, that could be Fisher Street there then as well.
He's not actually going up Fisher Street. Yeah,
he went along Fisher Street.
He went along. That's the only one along that he nearly collided with, perhaps. Or maybe here too.
That's what I'm thinking.
So it's probably
that
this corner that they turned around. And he went past all three churches.
Traffic lights.
So
I've got another clue about a phone box because we need to find telephone. Some kids in a phone box saw it speed straight through a red light.
There's a telephone.
And is there a traffic light?
You can see that this group is still concentrating after having spent quite a long time on the task. This is an example of one of the advantages of group work. Students' willingness to persevere longer at an activity when working together than they would by themselves. So you can give them more challenging activities to do in small groups than you could individually.
I had to go past a church. Went along that way, back here, joined Fisher Street, up here, past another church, went down here,
Traffic lights.
I've got another clue about a phone box because we need to find telephone. Some kids in a phone box saw it speed straight through a red light beside them. So we need the phone box, telephone, and a traffic light.
Have we got any more street names though? Because my next card is a red herring. This is the car had to wait at a crossing as the train pulled into the station.
Need to get up to Fisher Street. So
Got to go
probably
past
up
the
here.
primary school there.
Oh yeah, but we can go up this way and then past the primary school.
We'll get a highlighter.
It was travelling west at the primary school.
So you want it to go
little bit here.
this way?
Yeah.
Here, and then along here, up here. Is that right? That was the number 6 bus that went
And we
this way.
just said, well, bus route, yeah, we didn't see it.
Many teachers have used these two problems with their students successfully, but definitely not as an introductory problem.
Why don't we compare
Here, up there, down there,
Through the lights.
along here, along there, and that way.
come back.
Turn left at the hotel.
And that's where the number 10 bus is.
Okay.
The bus route.
No, it's Fisher Street, they collide.
Yeah, which is there. But where's the bus? That's the bus route there. So Fisher Street
Is there more than one right answer?
It's the number 6 bus, is it?
Yeah. So we thought it was that hotel. We saw that one, but didn't see it on the corner. Yes.
We argued for ages about right what's on the corner.
Near the corner.
There's a few things that we should say about the strategies of having movable things. One reason is that there's a problem-solving strategy that involves moving things around, which we sort of call guess and check or trial and error and things. So people shouldn't be afraid to try things out and maybe it'll be wrong and we just move it. It's more difficult when you've got a pen because you're committing yourself onto the paper. And so that's why it helps to have movable pieces because you're not afraid. You can commit it, but you can move it. So encourage people to go straight onto the map, try it out. It's a strategy. It's called guess and check. Other examples that I've included in the Velbeck resource deal with numbers and their properties. There's one series called What's the Secret Number? In these, students use the clues to find 2-digit whole numbers. The manipulable pieces, the bits that move around, are the single digits 0 to 9, and the clues describe the properties of the number the group needs to find. These are excellent for reinforcing place value and the language of numbers such as odd, even, less than, greater than, total, etc., as well as developing problem-solving skills. Another set of similar problems at a higher level is find the decimal number. This focuses on decimal place value. There are now 7 problems in each of these series. Problems like these can be used in several ways. Once students understand the cooperative logic structure, they can be used as a focus activity. By that I mean something to get students settled and concentrating, working together at the start of a session. One of the things I do with students to get them to extend the language, they've been understanding the language, but they haven't used it. So one thing after that they've done several of those simple map things would be to get them to create a problem themselves. Then we go from reading the language to having to use it themselves. They've got all the models there, they just have to use them and create their own sentences. And then they pass it on to another group to solve. That gets very interesting because students really like to make it hard so the others can't solve it, but you have to say that they don't win. If nobody can solve the problem, they're not winning either. A successful problem is one other people can solve, but it's a good strategy to get them engaged in the language and the language structures. In the workshop, we did this extension activity using some 3-dimensional problems called build-its. These involve creating structures with colour blocks and developing students' 3-dimensional spatial language, such as on top of, below, behind. First, the group worked through 3 of the existing problems.
There's 6 blocks in the yellow one.
Yeah.
The green block shares a flat side with all other 5 blocks.
These two work because they share one edge, the blue one with each of the red, and the 2 edges don't touch each other, so that's okay.
2 blocks aren't touching each other to the 2 blue
Later,
ones.
they created their own problems for others to solve. Sometimes extensions like this can help you cope with a mixed level class. You ask the small groups who finish early to do the extension. That way, everyone can be gainfully occupied on similar content. The new problems they create can be tried out by other students another day.
There is only one of each colour.
No 2 blocks.
No 2 blocks of the same colour. Yeah. Like that.
The next day, they watched while other groups solved their problems. They reported that actually being on the spot and seeing confusions or uncertainty created by their clues helped them to spot errors in expression very quickly.
That. Is that too hard to describe?
We should be able to do it. We need to be very clear about our definitions,
Is that
wouldn't
too
we?
hard though?
They were talking. The other ones talked about sides and edges, didn't they? And faces, face, side, and edge.
May I reiterate something which I didn't say before? If other people can't solve it, this is a good problem. It's a bad problem. Okay, but I noticed this tendency with students to always try and make it harder than the ones they were given so that they'll challenge the other group. So was your language influenced by the clues that you had in the first place? Were you using similar? So that is the point of getting students to write their own, because not only if they had to understand the language in the original clues, then they have to start using it for themselves. So then they'll start to own that language. And of course, it's working together, so it's not threatening to have to use it by yourself. This video demonstrated some examples of the very particular structure of problem solving called cooperative logic. It's designed specifically to encourage students to interact and discuss numeracy ideas in small groups. Just like the other activity models in the series, it can be applied to teaching a wide range of topics and their associated language. The possibilities are infinite.